So I'm going to share my screen now. And can you see my screen?
Yes.
With the lecture and the terminal on the side?
Yes, we see both.
And is the font okay for the terminal?
It is fine for me.
Okay, then. Otherwise, please write in the chat or in the document, and we are going to adjust things as we go along. So, so we come to the second lecture of this course, which is basic concepts. And please allow me to introduce myself again. So I'm Diana Iusan. I'm working as an application expert for SNIC, which is the Swedish National Infrastructure for Computing that HPC2N is part of. And I am going to use actually both the slides and the terminal a bit further on during the course. And as I said, I mean, please let me know if you don't see things as it should be, and also if I'm going too fast or too slow. And if it's perfectly fine to type along if you have the opportunity. Otherwise, it's also okay to just watch the slides and maybe try these commands later today or the coming days. So it's up to you. I may say that if you are a total beginner to Git, this may seem a bit overwhelming, but please understand that you are not intended to memorize all these commands that I'm going to show you now. And if you don't understand all the tiny details, that's perfectly fine as well. We are going to get back to these concepts and commands in the following lectures as well. And it should be become more clear as we move along. And the sole goal of this lecture is to understand some basic concepts. What are hash sums and blobs and trees and so on. So that's what we are going to do. But yes, and actually these concepts are going to understand this concept is going to help us understand what the Git commands actually do. So first of all, what is Git? So Git is nothing but a distributed version control system. And what does distributed mean? It means that it does not rely on a server client model, which means in practice that everyone that is using Git has a full copy of the entire project, or the way we refer to it in Git, the entire repository. And the advantage is that it contains the entire history of the project. People can work completely independently on the project. And well, in practice, this just means that you don't have to wait for anyone else to implement the changes before you can actually start to do yours. So everyone can work, as I said, completely independently on the project. And it is optional to set up a server in order to distribute the changes. And we are going to discuss this on Thursday and Friday, how one can do this. So why do we want to use it? Why do we want to use Git? So Git is among the most popular version control systems available. And maybe your colleagues or collaborators are using it already. And this is already a good enough reason to use it. And you may also want to contribute to the project as well. It relies on hash sums. And what is a hash sum? So a hash sum in simple words is just a string of characters which has a unique correspondence to the contents of a file. And two files which have exactly the same content have the same hash sum. And the advantages of using hash sums is that you have built-in data corruption detection and security. And I already mentioned that the Git is distributed. Other advantages of Git is that it's fast, simple, and flexible. system. It's also free and open source, and this is probably one of the biggest advantages. Maybe you as a researcher actually don't know, or your supervisor does not see the value of paying for a tool which is too expensive, and it works great. So let's move on and try to understand how Git stores the history of the project, or well, the repository. In order to understand this, I'm going to actually create a Git repository. So I'm moving back to my terminal on the right-hand side, and I'm going to create a new directory here, and I'm going to call it a repository, which is not a terribly good name, but it is actually our repository. So maybe for this very first exercise, it's good enough. So I'm making a directory. I'm going to move into this directory, which is called repository. And right now I have nothing in this directory, but I'm now going to initialize this repository, or this directory called repository, into a Git directory. And the way I do that is using the Git Init command. And by default, if I don't specify any additional argument, it's going to take the current directory that I am in, this working directory, as my Git repository. So I type git in, and you're going to see there is a lot of verbosity. One remark is that how much verbose output you get may depend on the version of Git that you're using. I'm not sure if it also depends on the operating system that you're using. But if you do not see exactly the same output, then you do not have to worry. So what it tells me is that actually Git has initialized this repository, and then it prints the full path of this repository. I also get some warnings that that I may wish to change what the branch is called, but we are going to get this later on. But by default, for my operating system and this particular version of Git, the branch is called master. If you don't know what branch is yet, don't worry, we are going to get back to it later on. So, but what we should take from here now is that now I have initialized this Git repository in this directory called repository. And so we have now a hidden directory, which is called Git, and I'm going to show it here using the ls-a command, which shows the hidden files. You probably know this already. So we have this Git directory here. If I do now tree, which is a command that gives a nice ASCII representation of my tree directory, then I see that well, I have no files here. I'm going to do a tree and the argument Git, and then I can see the entire structure of this Git directory. And we are going to go a little bit into what all these files are. I also have a graph representation of this directory. It's basically the same as I have in the command line. And so there are 3 files which are in this Git directory: the head, config, and description, and also the rest is different directories which are more or less interesting. Most of them are actually empty right now because we have not done anything yet. So in the config file in the Git directory is just a series of configurations that one may change. I have to be honest with you, I never change this config file. For my purposes, the settings which are done by default work perfectly for me. And then the head file just points, it contains some references that we are going to get to later on. And then we also have a file which is description, and one may edit the description there, but actually if you sync this file then to a repository on GitHub, then this is going to be updated. As I said, I almost never edit anything in this Git hidden Git directory. Everything is going to be done by the Git commands that I am using. So, and that we are going to learn in the following. So let's add some some content to our Git repository, and I am going to create a new file txt, and using the echo command, I'm just going to input some content into this file. Let's say that this file is very interesting, and I'm going to write exactly the same content as it's in these slides, and it will become clearer later on why I actually do this. So this file is very interesting. Maybe not so, but it's good for explaining. So, and then when I see here, I have now a file txt. Now I will use the git add command with the argument file txt, and what this does is it's going to tell Git this file exists and please keep track of it. And so I do that. And now if I look at the tree structure of the Git tree, I see that as I have added this Git file, as I have added the file txt, I have new files in the object directory. It's so under the object directories, there is a new directory called 09 and name which looks like a string actually, and what that is. So what that name is well, nothing but the hash sum of the file that I have just created. And before I explain more on that, I will also commit this change. So by using the git add command, I have told Git that please please track this file and add it to the index or staging area, which means that which is basically an area that will include all the changes that we want to commit. And let's assume I want to commit these changes in the newly created file txt, and I do that by using the git commit and then -m and the commit message that I want to use, and I am going to write just this is the first commit. And then enter. And what happens here is that I now got the first commit, which has a hash, which has this hash, and actually this is just the first 8 or 9 strings of this hash sum. And if I investigate the tree directory again, so tree and Git, I see that I have a new object file there created, which contains these which has objects which have the same name as the hash sum. So first of all, they are the first 2 strings of the first 2 characters of the hash sum, and then the rest of the hash sum follows. And why it's split? Why is this string split into 2 and the rest? It's just because we don't want to have too many object files in one directory, and this is one way of creating some several directories to manage this a bit better. That's just the only reason. And then if here we have also the same illustration of our Git tree. We have some newly created objects, as I said, in this directory. We had the initial one, 09, which corresponds to the object of the file txt. And then we have some new ones which are the 1A and the 2051. So you may have noticed here that actually the names of the newly created objects do not match what they have here, and I will explain this in the next slide. So before I do that, I should just make clear that everything that we have in this directory, which I have called repository, with the exception of the hidden Git directory, is part of the working tree, sometimes called the working area or the workspace. And then, yes, I mean, at the very moment, we only have one file in this directory, and this is the file txt. So we have seen that these files are stored in Git as objects. So the file txt is stored as this object in directory 09, and then a string name. And Git uses content-based addressing for storing the content of the files. So what does this mean? It means that instead of using the name of the file in the object, so it would have used, like, for example, file txt, Git is going to use a hash sum instead, which is a unique identifier of the content of the file, in this case, the file txt. So in other words, what Git is going to do when we write Git add is going to compute a hash sum from the content of the file. And it's also, as I said before, it's a unique string for a given content. And also two files which have the same content are going to have the same hash. And the Git is only going to store that once, even if there are two files which are identical. Okay. So we may also compute this hash manually. So maybe this is a good exercise. So for example, if I type Git and then hash object, and then file txt as argument, then I see this hash here, which is basically the same as was created under the objects directory. So we have gone through this, so you can actually see this in the Git tree. So let's do a short exercise here and show that the two files which have the same content have the same hash sum, and I'm going to just copy then the file txt to a file 2, for example, and I am going to use the same command here with both files, and then I see that these two have exactly the same hashtag. These two files have exactly the same hash sum. And actually, I'm going to remove it immediately. This was just for the sake of showing you this. So let's see now what. So there are other ways to see the content of the object in the Git directory. So I can use the git cat file command with the option -b, which means show the content of the file, and then the hash of that object. And then I just copy part of the hash. So please note here that I do not need actually to write the entire hash sum. So it's enough if the hash sums in the object directories are different up to the string that I have printed, then it's going to find them. Otherwise, I mean, Git is going to complain. It's going to give an error message that there are several objects that match the part of the hash sum given. So we saw that so this outputted as given as output the content of the file, which is just this file is very interesting. And if you are working on a very large project with many different object files, then you may actually need to write more hash sums if you use these commands, but that's really just for very large projects. Usually 7 or 8 strings are fine for identifying the objects. So these objects should not be accessed directly. Sorry, these are binary files, but using the command I have shown, one can see the content of the object. One can also see the type of the object, and I'm going to exemplify this in the following. So instead, sorry, I'm going to remove part of this hash sum. So I'm going to change the option from -p to -t, which means that please output the type of this object. And in this case, it is blob, which just means a large binary file. So if, for example, I remove the file from my working directory, so you may see that now my directory is empty. If I investigate the Git tree structure, I see that the object which was associated with it, it's still there. So Git is not going to sorry for that. Git is not going to remove the object unless just by removing this file. This means in practice that we can actually restore some of the mistakes that we've done. Let's say that we actually did not want to remove this file. It was just a mistake. We can restore the file and its contents using the Git Restore command and file txt. And we may see now that this file is now back in our working directory. And the content is basically the same as we had before. So, so if we have another look at our repository, in this illustration or here in the terminal, we see that there are 2 additional objects besides the one which corresponds to the file txt. So what are these 2 objects? In order to find out, I'm going to use this git cat command again, cat file -t, and then the hash sum, so 1a. So what I see is that this is of type tree. So basically what this object points to is the tree structure of my repository. And the other object that we have created, or what was created by Git when we used the Git Commit command, is this one, and this is of type commit. So basically, this object points to a commit. And let's see the content of this object as well. So I see that we have a pointer to the tree object, which is the same as has the same hash sum, obviously, as I have shown before. And we have some additional information on the author and the committer of the commit. In this case, it's me, and then also the time in some format which is not easily recognizable. And then we have a blank line followed by the message of the commit. So if you remember, when I have committed the changes to this file, I actually included a message. This is the first commit, and this is what also shows in the objects file of the commit type. Okay. So in our particular case, the tree only has one level. This means that we actually do not have any subdirectories, and it also has one blob, but this is because we only have a single file in this repository. So the tree points actually to this blob, which has the content. This file is very interesting. So let's take a further look at our repository. There is one object only that remains there, and oh, I think I actually skipped a bit the object for the tree. So I'm very sorry. So I'm going to show that instead. So if I so the object 90E50 was actually for the commit. If I use the cat file command together with the T option for the object 1A, I can actually, let's see, we can see what the type of that object is. And the output I get is, it's actually a tree, and that is going to show us a tree structure. Oh, I did show that. So sorry for the confusion. I'm a bit out of sync with the slides. So what does a commit do? It does nothing but store the state of the project at a given point in time. And in our case, the commit points to a tree, which in its turn points to a blob, which is, and if we look at it from the point of view of our repository, so we have a metadata, which is the metadata of the commit. We have, which points actually to the repository that we have, and in that we have for the moment the file txt. So in general, the associated tree actually can contain several levels and multiple blobs, which means that we can actually have different directories and subdirectories in our repository, and multiple blobs, well, that just stands for multiple files that are present in our repository. So let's get back to the repository, the illustration of our repository. So we have talked a lot about the objects directory, and which contains the objects for the blobs, the trees, and the commits. What we also have are two important one important file and one important directory. So the head file and the reference, the refs directory. So head and refs. If I am to paste the content of the head directory, sorry. I see that this points to a reference which is called master. In its turn, the master reference points to this hash sum, and if you remember, this is the hash sum which stands the hash sum of the commit that we have just performed. So it's this one here. So the head in this particular case points to the master, which points to this commit, and in its turn points to the tree object, and points to this blob object, which stands for the content of the file txt. One note I should make here, that you may see that the number of the commit here does not match actually the number of the commit that I have, which is 95 and so on. And there is a very simple reason for that. It's because the content of this commit object is different in my case. And the difference is actually the author and committer, and also, well, the time. Otherwise, well, everything else is the same, but because this content is different, then I am going to get a different hash sum. But the rest is the same because I have the same tree structure. So the hash sum of the tree object is identical to the one shown here on the slides, and also the one of the blob, because the content of this file is actually identical to the one we used in the example in the slides. So head and master are references, and we can but a reference points to commits and other references that we are going to learn about, and head typically points to the most recent commit. And we are going to go through some example when that is not the case, but most typically, most recent commit is actually the head. And why we need to understand the head reference is that many commands which we are using act on the current head. So we are going to get back to this in the following lectures as well. And master, you may have realized by now, it's the current branch. So, or for those of you that don't know what branch is yet, is, well, our main line of development for this project. And we are going to go again more through what branches are and how we work with them later. So instead of using this long hash sum for our commits, we can make some references to these commits. And the way we can do that is by using the command git tag. And as argument, one should then choose a name which makes sense for this particular commit. I may call it version 1.0 or 0.1, or in this case, I'm just going to give it the tag first. And if I investigate the tree, the Git tree again, then I see that I have created some new files, or updated files under references. So the new file which has been created actually under this directory, refs and then tags, is this first, and we'll see shortly how it looks. So it's also exemplified in this illustration here. So under the Git tree, we have the refs directory and the newly created directory tags and the file first, which is the reference for our newest tag. So let's use the Git ref parse command together with the argument, so the name of the tag that we have just created. And I see that I have misspelled. And the output of this command is actually the hash of the commit that the tag first refers to. And this is identical to the commit object that we referred to before. So the tag first actually points to the commit, which in turn points to the tree object, which describes the directory of the working directory. And then in its turn, it points to a single blob. In this case, as we only have one file, and that is the file txt with content, this file is very interesting. So we are going to move to the index or staging area, and I'm wondering if we need to take a break at this point. This may be a good time to take a break if you want to.
We should probably take a break, because otherwise we will be very much ahead of time, and someone may decide to join for specific parts of it. So.
And then I can also check the questions in the document and maybe refer to some of them. So okay, then let's take a break now. Okay, then let's start again. So index, or the staging area, is yet another important concept to know about in Git. The index, or the staging area, can be best understood as an in-between area between the working directory and the commits. The index actually contains all the changes that you have made in the working directory, which you wish to include in the next commit. And to understand this better, let's modify the content of the file, txt. So I will use echo again, and I will add another line, more content, and append it to the file txt. And now the file is like this. So we had the initial line, this file is very interesting, and more content. And what I want to do in the following is to tell Git that, okay, I am happy about the changes that I have made to the file txt, and I want to add these changes to the index, or the staging area, as I plan to later on commit them. But I don't commit them yet, I just inform Git, these are the changes that I have made. And I do that by using the Git Add Command again. And as argument, we have the modified file, in this case, txt again. And I'm going to use the tree command again to see the Git tree structure. And some of you commented that you don't have this command. You can also use ls, for example, to just go through the tree. And yeah, but otherwise it's also relatively easy to install. But then again, if you don't have it, ls works too. And then you will see that we have an additional file in the objects folder, and that is the one with the hash some 3b23 and so on. So it's this one. Unfortunately, my tree doesn't list the most recent at bottom. It's quite tricky as well when it comes to trees. So, but this is the new object that has been created under this Git directory. And you may also see it here in this illustrated tree structure. And also red is what the file text is in red because we have actually made changes to the file. And in order to see the contents, I can also use the alternative git cat command, cat file command. So this will print out again the contents of this binary file, which has the hashtag freebie. Let's see, freebie. I'm going to copy paste some of the string from here. So we see that the content of this binary file is this file is very interesting and more content. Okay, so far so good. So in other words, we have a blob, well, a new object which refers to this modified file txt. You may notice that the original blob that corresponded to the file txt is still there. And the reason why there are two different blobs to the same file is because simply they have different content. And as we learned before, there is an identical hash sum for a given. So there is a unique hash sum, sorry, for a given content. There are no other objects created there yet, because the only thing that we did was actually to modify the file. So we only created a new object, which is actually of type blob. I will just confirm it using the -t argument. So indeed, I mean, this object is of type blob, which corresponds again to large binary file. So the command git add tells Git that it should add this file to the index or the staging area. And then this way, Git is going to be ready to include it in the next commit when we decide so. And the index actually contains a representation of the tree object. And it's a binary file. And now let's say we are happy with the changes that we have done, and we are going to turn the index into a next commit. And we do that by using the Git Commit command and -m and the message that we want to use for the commit. And I am going to give it the message, this is the second commit. So typically, when you commit your changes in the directory, it's good that you give good descriptions of the changes you have made in the commit message, because this way, when you come back in a few months' time or a few years, if you want to know what you have included in a certain commit, this is the best, one of the best ways to see that. Okay, so this is the second commit. And then we have here a shortened hash sum of the commit object. So C7, so on. We can also see it I will copy it first using the tree command. So here it is, C7, OF, and so on. Okay. So the additional objects that were created after the commit are the object of the commit, and also the object which corresponds to the tree structure, and that is the 22b5 here. So the D3 is the commit object, and this one is the tree object, which I also have here in my tree, as the tree structure is exactly the same in my directory as in the exercise used for the slides. What is new is the one for the commit, and that is because the committer is different, and then the hash sum is going to be different. Also, if you do this example yourselves, you are going to get a different hash sum for the object. Okay, so we have a tree object that describes the directory structure. I'm going to confirm. Well, let's check the content actually of it first. Cat -file and -p for printing out the content of it, and the hash sum of the object. So first 2 characters are in the directory name, and then some more to correctly identify the object. And we have, so in the content of this object, which is of type tree. So if I type -t, we actually see that this is an object of type tree. What does it contain? It contains a line identifying a file name, in this case the file txt, the hash sum which corresponds to this file. So it's the freebie1, which we have just created, and the type of the object, and this is a blob, which again is just a large binary file. And we also have the commit. So let's look how that contains, what that contains. So cat file -p and the hashtag of the commit, and I just scroll up and copy it from here. So it was included in the output when I committed. So git cat file -p, and then I see again that the commit points to several things. One of them is the tree object, and we have seen what the tree object contains. It also points to the committer, the author and the committer, and we also have the type on the right-hand side, and a blank line followed by the message of the commit, which in this case was this is the second commit. There is one additional line in this in the content of this object, and that is the parent. So parent followed by a hash sum. This is actually just the hash sum of our previous commit. You may have recognized it from before, so it's also included in the objects directory. So yes, so this is the major difference in this new commit object, is that it actually has a pointer to a parent commit. And we can illustrate this here. So our latest commit, the second commit, which points to a tree, a parent, and author. It has two. It has the parent commit 23B. In my case, actually 95, which also points to this tree object. 1A, which in its turn points to the tree object. Yes, I said 1A, and then that points to the file blob, our initial file. So our second commit points to the updated tree structure, which has a different hash sum because the content is different, and then again to this updated a file which has a different hash sum 3B23. So when we develop a project, we usually have a series of commits. We have a large commit tree, and this is one way of representing it. Here, the structure is linear. We have an initial commit, which is commit 1. And then as time evolves, one may include more and more changes and actually gets to newer and newer commits. And every commit is going to point to its own tree structure. So we have different tree structures for different commits. And again, I mean, each commit actually represents the state of the repository at a given point in time. And the tree objects are actually a representation of the state of that repository. So in the example before, we have seen that we have shown a linear tree structure, but that does not have to be the same. Actually, a commit can have multiple parents. In this example here, commit 4 has 2 parents, so it points to 2 commits, the commit 2 and the commit 3. So when can we have these multiple parents? Actually, this happens when 2 or maybe even more branches are merged, and we are going to discuss branches and when they are useful and how we work with them on Thursday. Okay. So let us move back to head and other useful references. And the head in our example, so in the current state of our repository, it points to the master branch, which points to the most recent commit, which is the second commit, and then that in its turn has the parent, or it points to the commit before, which is the first commit of our repository. So I can also show this from the command line. So if I want to know where the head points to, then I can just cat this git head. And I should make a comment here that when I'm usually working on a repository, I would almost never use these commands on the hidden Git repository. We are going to learn about other commands where we actually check what the head points to. But this is just to understand what Git does in the background. So just to be clear. And then I'm going to cat also the reps. So I'm going to see actually what, so I learned that head points to this reference master. And now I'm going to check actually what this points to in its turn. So it's refs, heads, master. And what it gives me is the hash of the commit which the head points to. And this is actually nothing but our second commit. And then again, this hash is different than what is printed in the slide, simply because the content of the committer itself is different. And I kept it this way because then, I mean, when you do this exercise, you will also see that that you get a different hash sum compared to what is listed here. So it's very important to remember that many commands actually act on the current head. And that's why it's important to know what the head, which commit does the head point to. So we can change this pointer or the head to something else. So it does not necessarily have to point to our very latest commit. Let's say we want to actually go back in time and see some changes that we have done a day before or a month back. And the way we can do that is by using the Git Checkout command. So Git Checkout, and then I need to provide this argument the hash sum of the commit. And actually, I do not remember what the hash sum of my first commit is, so I'm going to introduce you to another command. I want to just do git log, which lists all the commits that I have done in this master branch, and I'm just going to copy this hashtag. We will get back to this command in the following, so you don't have to remember it, but the point here was just to get the hashtag of the commit, because what I want to do is now to revert to the very first version, to the very first commit of this repository, and then I have to provide the hash sum of the commit. Okay, and then I'm going to actually get a long warning. We are going to get back to this. Basically, Git is warning me that the head is now in a detached state. We'll clarify this later on. But what Git Checkout does, so it reverts to the very first commit. That means that actually it's going to change all the files in the repository to the version that they had of that particular commit. So if I type now cat file, I can see that I am missing this more information or what I had wrote in the second commit. I am only having the contents which were committed in the very first commit, or which were registered in the very first commit. And let's see now where the head points to. I can do that by using cat git head, and this is going to give me this commit hash. And if you check now a bit higher up, this is just the hashtag that I had for the very first commit. So it's a hashtag and sorry, the hash sum, I should say, and then the message was here, the very first commit. Okay, and we can also look at the illustration here. So after the checkout, the head, so the pointer has moved from the second commit, it has moved actually to the first commit, which has, in my case, the hashtag 90E5 and so on. And it also points to the tree structure that was at the very first commit, and then we also have the author and committer, and the master branch. Now, well, it consists of the two commits that we had, the second and the first commit, but it is but the head is basically no longer on this master branch. So how can we modify this working tree further and create a new commit? So I am going to, remember now the head is pointing to the very first commit that we have done. And I am going to modify then the file.txt by adding an additional line. So this is going to get appended to the file.txt. And I am going to add this modified file. So this is the way it looks like, cat file.txt. I am going to add the modifications of this file to the index, or well, the staging area, and then I'm going to commit it. And I can do that by typing git add file.txt. So this adds the modifications to the index, and then I can commit it. Commit the sham and some commit message, and we are going to keep to this flow and just name them as in terms of the numbers. So this is the third commit, let's say. So you may have noticed that in the slides there is a different command, and I have written it, I have typed different commands on purpose. So what I have done is to first do git add file.txt, which stages the file, and then to actually do the commit, which then takes the modified changes which were indexed, so in the staging area, and I turn them into a commit with this hash sum. One can also do, so one can combine these two commands, the git add and git commit, into one single command, which is git commit -a-m, which means that Git is going to both stage all the changes in the working directory. It's going to stage them to the index, and it's also going to commit all these modifications. So this is just well, shooting two birds at once. So basically it's just adding and committing in one command. And I should comment this is perfectly fine to do if you do not do many changes. If you have changed several files and you do not want to incorporate all your changes into the commit, then you should avoid using these combined options. Okay. So then let's investigate now this newly created commit, and the hashtag of this commit is written here in the output of the command. So I'm just going to copy it, and I will use again the git cat file command with the argument the hashtag of this commit, which again it's different from the slides because the author is different. And I see that this commit points to different objects. So one of them is the tree object, which represents the tree structure, and it has this particular hash sum. It also points to a parent commit with this hash. And then we also have the information on the commit, like who has committed and what was the message of the commit. So again, this is just a representation of this third commit. It's pointing basically to the parent commit. This was the very first commit that I have done. So if we think of the entire commit tree structure that we have actually now two branches. We have the initial branch, which was called the master branch, which contained the very first commit and the second commit. And we also have our new branch, which consists of the first commit and our most recent commit, the third commit, which has the parent, the first commit. And actually the head points now to this third commit, and I can actually double check that. So if I do cat git head, then I see that the commit has this hash, which is identical to the one here. So this is the one I get when I commit the changes. So up to now, I mean, this branch actually does not have any name, and it would be nice to refer to it by a name instead of just a series of commits. So let's do that using the Git Checkout Command, but now with different options. And you will see that actually Git Checkout can mean many different things depending on the arguments that it has. And you don't have to remember these commands now. We are going to get back to these, but for the moment, just watch along or type along if you do so. So Git Checkout -b and a name of the branch. And what the option -b does is it tells Git, please create a new branch, which is called second branch, and switch to it. So now we have this new branch called second branch. And if I check the Git head file again, so before it has actually pointed to a hash, but now if I actually type the content, I can see that it's actually pointing instead of a commit, instead of a hash, it actually gives it the name of the branch. And if I refer to this file further, git refs heads second branch, then I see that the head of this second branch is actually my latest commit with this hashtag. Okay, so so now we have two branches. We have the master branch, and we have this second branch, which we have called second branch. So this additional branch, which we have called second branch. So we can actually merge these two branches in one main branch or one master branch. And we can do that with a series of commands. So the first one is Git Checkout master. What this means is that, sorry, not Git, not get, but Git. So it's going to switch from the branch that we are on to a new branch which we wish to be master. So first I'm switching to the Git, to the master branch. And then in order to merge these two branches, master and the second branch, I'm going to use the command git merge --no f, which means no fast forwarding of if there are conflicts between these two branches. And again, this will be clearer on Thursday when we go into branches in detail. But for the moment, the command is git merge with some options. So this means merge this second branch into the master branch. And I am actually going to get an error message, automatic merge failed. And that is because actually there are conflicts in the file txt contains different content in these two different versions, and it is conflicting. So let's now edit the file txt. And I see here that actually what Git has done is to incorporate the changes in the two different versions, in the second and third commit, into this file. So in the third commit, that the head was the head is on the master branch, which is the second commit. So in the second commit, we had added the line more content, while in the third commit, which was on the second branch, we have added the content, different content. But now what we have to do is, because this line, well, these differences were in the same line, Git is telling us you need to choose which modifications to this file you want to keep before I can do the merge. And then I am going to keep one of them. It doesn't really matter which one you keep. You can also add entirely new content. Maybe you want a mix of two. You can say more and different content if you really want to. And I'm going to save this file, and then I'm going to merge these changes. Also, first of all, I have to stage the changes that I have done in the file txt. Otherwise, Git will not know what it should commit. So before I commit, I need to stage. So let me rephrase. Whatever I want to commit, I have to have staged first. So I'm going to add git add file txt, and then this has staged the modifications in this file txt. And in the following lecture, we are going to learn more about how we can see the status of these different files. So you actually do not have to remember by heart, oh, what did I change and which files did I change? But I'm not showing them now because it would be too confusing. I just know I have made changes to this file. I'm going to include these changes in the file to the index using the Git Add Command. And now I'm just going to continue the merge of these two branches, the master and the second branch, using git merge and the option -- continue. And then I get prompted with with the editor that is asking me actually to edit the commit message. So if you see here at the bottom, actually the file which is being edited is the commit edit message. And I'm going to keep it as it is and just save that. Okay. So let's see now. Let's investigate this object of the commit. So cat, okay, git cat file, and -p and the hash of the commit, which I will just copy paste from here. So I see that what we recognize the regular pointers to the tree structure, and this corresponding hash sum, the committer, the commit message. So it was just git, merge branch, second branch. And we have actually, instead of one parent as we had previously, we actually have two parents. And these two parents are just the heads of the, well, I should not say heads, but the latest commits of the master and second branches. It doesn't have to be the second commits, but basically there are two commits that were on these two branches. So this is how the tree structure looks like. Again, we have the head pointing to the very last commit, which was the commit that merged these two branches, the second branch and the master branch. And also we are on the head is pointing on the master branch because we have chosen to be on the master branch when we committed all changes when we merged the changes from the latest commit of the second branch. And using these dash lines, we can also see the pointers to the tree structure, and also the pointers to the files which the trees are pointing to, or the tree objects are pointing to. Okay, so we can revise this Git Checkout command again. So again, I mean, if I do want to revert back in time, I can do that. Maybe I want to investigate the changes that I have done in a particular commit. So I may do so again by using the command Git Checkout and the hash of a particular commit. And actually I don't remember this by heart, so I will use this git log command again, and you are going to be introduced to it in the following lecture, so you don't need to know it by heart. But let's say I want to revert again to the very first commit that I have done, so I may do so by typing git checkout and the hash of that commit. Of course, it doesn't have to be that particular commit. I can revert to either the second or third commit. That's entirely up to me, depending on what I need to do for my work. But for the sake of this example, we can revert to the first commit. And then again, I'm entering a detached head state, and I can check the contents of the file txt, and it's again, this file is very interesting, which is the content of the very first commit, the commit that I have pointed to using Git Checkout. Okay, so with this, we actually get to the end of this lecture. And I know that there are quite a few new concepts that were introduced. Maybe it was not so easy to follow, but we are going to go through actually all the basic commands in the following lectures as well. And I hope that when you use those commands, then you can also have a better understanding of what Git does in the background. So I will quickly check if there are some questions in the Google Doc. Otherwise, you may also write them now if you haven't written them